Welcome to Chapter 7. In this lecture, we're going to discuss quadratic and interaction effects in multiple linear regression. In this lecture, we want to talk about how to control for some portion of nonlinear relationships. In this case, we want to control for the relationship between the dependent variable and the independent variable that are nonlinear in a quadratic or some other similar way. This is useful when the scatter diagram indicates that the relationship between your two variables, your dependent and independent variables, are nonlinear. The most obvious example is a quadratic model. In this case, we have our dependent variable equal our independent variable and our independent variable squared plus the error term. The second independent variable is just the square of this one, so you just square this to create this one. We can also have polynomial regression models where instead of just squared all the way to p, where p is the order of the polynomial, I tend to just cut it off at a quadratic, but hey, up to you. Here is nonlinear fits, and so if we look at the residuals, so you can obviously ask Excel to give you the residuals. If you plot those residuals against your x, if they have this nonlinear relationship, you may want to think that there's a nonlinear relationship between y and x. Whereas if you fit this quadratic, then the residuals are like you want them to look, which is totally random. I don't really do this kind of residual analysis that often. I tend to just do the scatter plot and see what's happening and see what model is best for me to fit. We can have different types of quadratic relationships. Here are the different types. Again, I don't typically worry about it so much. Let's just worry about fitting a quadratic regression model. Okay, so in this case, we have our y hat, our dependent variable, predicted value, equals the intercept plus the slope on xj plus the slope on xj squared. And again, this does not come pre-created for you. You have to make it yourself. You just, in Excel, do xj times xj, or that column times that column, and then that comes to the square column. To figure out the marginal effect, it's actually a partial derivative. And so you take the partial with respect to this, over the partial with respect to the variable you're interested in. You don't have to be able to do this kind of these kinds of derivatives. I've already given you these formulas. You can just copy it down on your cheat sheet. This is what it'll always be. If I take this partial with respect to this, I get beta 1 hat plus, and then the 2 comes down, so that's where this 2 comes, to beta 2 hat times xj. In this case, notice that once we have a quadratic or nonlinear relationship, to be able to figure out the marginal effect, it's a function of the variable that we're interested in. And so our marginal effect, unlike just fitting a line where the marginal effect is constant, in this case our marginal effect is not constant. Okay, so here's what it looks like. So basically, if we look at x1j, the marginal effect is the slope of a line tangent to this point right here. That's what the partial derivative does for us. And then we can see that, so here it's positive, here it's 0 at the very top, and then here the partial effect is negative. And so we can see along the different points of this curve, the partial effect changes, and it changes dramatically from being positive to 0 to negative. And again, the thing that I want you to realize or note is once you fit this nonlinear thing, where you choose to analyze this function is going to change the marginal effect, or how a 1 unit increase in x impacts our y. Here is my favorite, very, very favorite example of this. And it's your utility bill versus the temperature outside. So we can see if we if we do a scatter plot, this is the average bill per month, and then this is the average monthly temperature. We can see that this is a nonlinear relationship between these two variables. First, we're going to fit a line. So fitting a line is just having average monthly temperature. And if we look, we can see that it shows that there's no linear relationship between these two random variables. this is a large p-value. But if you look back at the scatter plot, it looks like there is a relationship. It's just a nonlinear relationship. Now let's fit a quadratic model, because that's what it looks like. It looks like a quadratic thing through these data. And how to do this, again, is just to square temperature and then do a regression. Your y value is average utility bill, and then your x value is both temperature and temperature squared. You can see that the R squared is very high at basically 92%. So we've explained a lot of the variation in utility bill using outside temperature. We can see that the F statistic, it's significant of F, this p-value is very small. And then if you look at the p-values for average monthly temperature and average temperature squared, they're both statistically significant because they're both well below even 0.01. Okay, now we need to talk about how to analyze this model. So here, if we just want to put in what this model is, utility bill, predicted utility bill is going to equal our intercept, 484.11, I guess it should have been, 12.08 minus 12.08 times this, average monthly temperature, plus 0.09 times temperature squared. To be able to figure out the marginal effect, we take the partial derivative of utility bill with respect to temperature, and we end up with this equation here. And then we're going to evaluate it at different values of temperature and see what happens. So, for example, we can see that the marginal effect of a temperature at 40 degrees, we're going to evaluate it at 39. So we're going to assume we're going from 39 degrees to 40 degrees. So one additional unit of temperature. We put 39 into this equation. We can see if you go from 39 degrees to 40 degrees, your utility bill will drop by, on average, $5.06. So again, we're over here in this equation. So if the temperature goes up, our average utility bill will go down. So we can see that's consistent with what happens in the picture. And then let's look at a higher temperature, 80 degrees. And so if we go from 79 to 80, we'll put 79 here. And we can see that basically for an additional unit, an additional degree, that the average utility bill is going to go up by $2.14. Again, the intuition here is when it's cold, you need the heat. So if it gets less cold, you're not going to run the heat as much. Whereas the opposite is the case if it's hot. If it's hot, then you're going to run the AC and your utility bill will increase. Sometimes, or a lot of times, what we want to do is figure out where our quadratic function reaches a maximum or minimum. And so to figure out the minimum of a well-behaved function or a maximum, you take the first derivative and set it equal to 0. We've already taken the first derivative, so you just set this function equal to 0. And we can see that utility bill example, the function reaches a minimum at 67.11 degrees. And so again, back here, you can see reaches a minimum right about there. So we can solve for where it reaches a minimum. So here's one example. Another example is, for example, if we want to figure out the optimal number of students to put in say in an elementary school class, we would want to figure out where test scores reach a maximum, so the quadratic function goes the other way. So we'd want to solve for that so we can tell policymakers how many kids we should put in a classroom, potentially. Okay, if we want to test for overall significance, we would set our basically everything that interacts with xj equal to 0, and that would be an F test. Or the other thing we could do is do a t-test and see if our quadratic term is statistically significant or not. One thing to note is once you put this kind of equation in your model, there's no way for me to hold temperature here constant, temperature squared constant by increasing temperature by 1. Once you have a quadratic or interaction effect, you basically have to look at both of these terms. So even if temperature is not statistically significant, but temperature squared is, you should put both of these in. If temperature squared is not statistically significant, then it would say that there's not a quadratic effect. But the main thing that I'm trying to say is I can't evaluate this term right here and hold this one constant. It's just not possible. That's why we have to use this formula. And then it's a function of at what value of our x variable we evaluate this marginal effect. So we can also have higher order models. So if our scatter plot looks like something like this, I find this is super rare, but you can definitely model it. The other thing that's related to the quadratic is interaction effects between pairs of quantitative variables. So in a different lecture, we talked about a dummy variable interacted with, say, comments or a quantitative variable. But here we're going to look at the interaction effect between two quantitative variables. And remember, interaction just means these variables are multiplied by each other. That's a weird interaction term, but it's just an example. Okay, so let's say this is the model we want to estimate. So this is x1, this is x2, and our quadratic effect, or sorry, our quadratic or interaction effect is x1 times x2. Sorry about that. And so basically, if I want to figure out the effect of x1 on y, I take the partial of y with respect to x1, and I get beta 1 plus, this term goes away because it doesn't involve an x1, but this one I'm left with beta 3 times x2. So I get this. And so when you have an interaction effect, then the marginal effect that x1 has on y will be a function of the other thing that is multiplied by, in this case, x2. Let's look at an example. And then, well, before we do that, this is just a hypothesis test to see if this interaction effect is statistically significant. It would just be an easy t-test. Okay, here's the example. This is the best example that I think for this. So we're saying that price of a house is a function of the number of bedrooms, the lot size, the square footage, and then bedrooms times square feet. Why would we want this interaction effect? Well, if you have a very small house, let's say 1,000 square foot house, adding an additional bedroom is going to have a very different impact on the price of the house, because that would just mean that, right, the price of the house, the square footage of the house stays constant, still 1,000 feet, but adding an extra bedroom means that your bedrooms are like closet size, super duper small. Whereas if you had, say, like a 5,000 square foot house and you added an additional bedroom, then it's going to have a different impact on the price. Here's how to create this variable. Again, you just multiply two variables together. That's what interaction effect means, bedroom times square feet. So I'm taking my bedroom variable, multiply by my square footage variable, and I come up with this new variable. And then I'm just making a little bit of a note that here, the price of a house is not $300. I mean, it'd be fantastic if it was. We'll have houses all over the place, but obviously it's not. So this is in hundreds of thousands of dollars. And then again, if we're thinking about a 4-bedroom, 2,400 square foot house in San Diego, it's not going to cost $300,000. So obviously these housing data are from some other market, not the San Diego market. Okay, so I ran this regression in Excel and I just ended up with the results that we care about here. We can see that bedrooms is actually not statistically significant once I include these other things. Lot sizes, square footage is not, but bedrooms times square footage is. And so here I just analyze the effect of adding additional bedrooms for different values of square feet. So the average value of square feet in my data is 2,014 square feet. That's the average size of a house. And so if I add an additional bedroom, then it's going to increase the price of my house by essentially $10,000 at the average value of square feet. I also evaluated it at 1,000. And again, what am I doing? So I'm taking the partial derivative of my equation with respect to bedrooms. So I get negative 33.71 plus, and then I get 0.02 times square foot. So that's the equation that I'm putting in here. And so at 1,000 square feet, if I add an additional bedroom, it's going to reduce the price of my house by about $12,000. And then here, if I add an additional bedroom for a 3,000 square foot house, it's going to increase the price of my house by about $32,000. This is what I was trying to say. is that the impact that adding bedrooms on the price of a house is a function of the square feet of the house or how large the house is. And if it's a small house, it has a negative impact. If it's a large house, it has a positive impact. Okay, let's do the opposite. Let's look at the effect of adding an additional square foot given or for the average number of bedrooms. So what am I doing here? I'm taking 0.03 and then plus 0.02 times the number of bedrooms. So we can see that for the average number of bedrooms, which is 3.57, basically if I have another square foot, the price of my house increases by about $112. If I have 2 bedrooms, it's about 77, adding an additional square foot, $77. If I have 5 bedrooms, adding additional square foot yields an additional $143 added to the price of our house. Again, the take-home message is once I have this interaction effect, I can't increase square feet by 1 and not increase this by 1. So I have to, these become a pair. And then same idea, bedrooms, and this becomes a pair. I can't increase bedrooms by 1 here and hold these bedrooms constant. Once I do this and increase this by 1, I have to also increase this. So these things have to be evaluated together. Thank you for listening. Hope this helped.